Cool. Okay, so the motivation for this talk is actually kind of similar to a lot of stuff we've been hearing about, so I'll just go through it quickly. I kind of like to start with some excerpts, my sort of favorite 3 sentences from the GNU Manifesto. So he says, a user who needs, this is like the dream, right? A user who needs changes in the system will always be free to make them. Users will no longer be at the mercy of one programmer or company which owns the sources and is in sole position to make changes. Schools will be able to provide a much more educational environment by encouraging students to study and improve the system code. I think the last one is even maybe my favorite of the 3. Yet, it's 2025. And we have so much free software. This is a free document viewer, Firefox. We have all of this stuff. But the thought of sort of casually studying and customizing this software, for me, kind of fills me with a kind of embarrassing amount of dread over this thought. And I think the answer is something that we've heard again and again and again through Onward the last 2 days, and that's complexity, right? So if we look at kind of, lines of code counts, I'm sure everybody here will tell me are not a good measure of complexity, but it gives you some sense, right? All these major projects we're using every day, it's, million plus lines of code. And this is kind of what fills me with fear of even getting started in reading some of these software. And I think there's a hope, I've at least always had this hope, that something like the STEPS project is going to work out, and somebody's going to invent just the right level of abstraction or kind of tower of languages that we're going to have, my whole Linux desktop environment in 20,000 lines of code, right? And I think what I've sort of slowly come to believe or accept is that this is not really going to happen. So users have a lot of righteous demands. They want their software to work the way that it's been working, right? I want Vim. I want my key bindings set up. I want my Vim script set up. And so just trying to use any kind of new rewrite of the software is already a hard sell. And on top of that, I think a lot of the complexity in modern software is essential, right? I mean, I think even you just try to, for a kernel, for example, even just trying to write, some driver software for some tiny, ADC chip or something, you got to go through the manual, and there's all this crazy, first you do this, then that, and everything. And so users want all these different combinations of hardware, software configurations, high performance, security, and reliability, and all of that stuff. I think we're sort of, at the end of the day, stuck with having some of our most important software be kind of incredibly complex in this sense. So the question is, if I accept that situation, what to do about it? And the point of this talk is to tell you about one experiment I've been doing for a couple months now and how it's kind of worked out for me. And that experiment is about documentation. So basically the pitch here is that documentation can help make software more understandable, and we can use tools to write slightly better documentation in this sense. So I guess I don't really need to go through these 2 slides, but without documentation, everybody who wants to start learning about how Firefox works or whatever has to do it on their own, right? But the magic of documentation is that whoever figures it out first, whoever spends a few days understanding, how Vim stores lines or whatever, can write documentation after they've learned it, and then share it with everyone else, and they can benefit from that knowledge, right? Okay, so basically writing is nice. Writing lets you share what you have learned with others. In practice, right, documentation is used all the time by programmers. And in my sort of mental model of the world, there are 2 styles of documentation that people use. The first is comments. Okay, and so comments, in my opinion, are great because they're directly tied to the code. It's like, yes, here is where the current line is set, right here in this code, and this is why. But of course, there are some bad things with comments. One is that, most of us write code in just ASCII text, and so it's very difficult to put real diagrams in there. Sometimes you load up some kernel header and you've got like a whole, ASCII art diagram somebody spent like 1,000,000 years designing, but this is kind of painful, right? And the other bad thing about it that's maybe more fundamental is because those comments are at a particular location in the code, it's very difficult to give a more global insight of what this code is doing. Comments are really about this chunk of code, right? So sort of the total mirror of comments is out-of-band documentation. So this is like a design doc or something. And these design docs are great because it can explain the global context, right? If people haven't seen it, you can go online and see like architecture of open source applications. You know, it explains the whole architecture of the system. It's not, you know, bogged down in the details. And you can make diagrams, right? Diagrams are great. They let me just instantly kind of see what's going on. But unfortunately, I've found a lot of this kind of design doc, out-of-band documentation to be kind of too high level. If I actually want to understand what this code is doing, you know, reading an architecture description gives me like a little hint, but it really is not, I don't feel connected to the code in this sense. Okay, so the whole project that I've been experimenting with is kind of how to bring these out-of-band documentation things a little bit closer to the actual code. And so I've been, you know, rolling with the name Literate tracing for this. It's not, you know, a totally new idea or something, but I think it's nice to have a name for it. And what I'm saying is Literate trace is a document that explains how a software system works by walking the reader through concrete execution traces of the system. So this is the whole pitch here, is what does documentation look like if it's structured around concrete execution traces of the system? So let's just answer that question. So there's a link here, which I guess if people have their computers out, you're welcome to just go to that link. And what you will find is this page, where I've sort of cataloged my experiments so far. And so let's see which one we want to start with. How about we start with this frequent words HTML link here, which, let me bring back my screen mirroring on this side. Okay, great. So this is a literate trace that's walking through a program that Knuth wrote originally to demonstrate literate programming, which, you know, if people want to go about the differences later, we can chat about it. But basically how this literate trace works is that it starts off talking about what the program does. So the program takes a text file and an integer k, and then it prints the k most common words in the file. And it shows a concrete input-output of running the program. So if you have this program here where k is 2, and then you have the xyz, xa, xa, it'll tell you what the 2 most common words in the file are. Then it goes through and does some, you know, relatively normal documentation stuff. It gives you an outline of the program. It tells you a little bit about the core data structure Knuth uses to implement this, which he calls a hash tree. And then, so after explaining some of that, we get to some more interesting parts. So here we're explaining how an insertion into the hash tree actually looks like, how it's actually done. And so you can see that in the middle of our explanation, we can actually jump into this kind of single-stepper block. Okay, and this single-stepper block is constructed from an actual running execution of the program. Okay, and at every step in the program execution, it updates this state visualization on the right here. Okay, and you know, something interesting about this program is that Knuth doesn't actually use pointers in any of this. He uses like a bunch of different arrays for all of the fields on the structs, and so each one of these nodes is actually an index rather than a pointer. I don't know. So you can walk through the trace here, and you can actually sort of see how all of these steps work, interspersed with prose. And so the key thing here is that, like, as you're reading this literate trace, you're actually seeing a concrete execution of the program. You're seeing how the program goes from the input file to the output file here. So we've made a couple of other, I've made a couple of other traces here that you may browse at your leisure. So for example, there's a few HTML ones showing, you know, how the hash map in GCC works. And, you know, one cute thing that you can see here is I've linked to where how they came up with the hash table. They did some sort of like empirical trial and error on things. In addition to this kind of HTML view, we also have a PDF output. So the original name of TReX came from tracing with tech. So TReX itself is actually just a LaTeX plugin. So let me see, for example, here's a LaTeX version of that previous trace. So you could, you know, print it out and read it on the toilet or whatever you feel like doing. And you can see in the tech here, we can actually step through piece by piece how different lines affect the visualization here. So that's the basic. I think with any luck at this point, you've got the idea of what I'm trying to do here. And just to give some, you know, a little bit more talking about what it is, you know, one big aspect of these literate traces are that there are system-specific visualizations, right? So the visualization of a hash table in GCC is going to be different from the visualization of a trie in Knuth's thing. It's also directly tied to the code. So in all of these literate traces, when you see some visualization, you also see where in the code that visualization came from. Another thing about doing this kind of literate tracing is that it makes it much easier for the author to skip over uninteresting aspects of the code. So for example, in the trace of the minisat sat solver that I did, I didn't want to get bogged down in explaining how like the heap is implemented, right? So minisat uses a heap, or you might call it a priority queue, to organize its variables to figure out which variable to decide on next. I don't want to get bogged down in like how it's implemented, but I also, don't want to leave the reader guessing what something like a pop does. And so the nice thing about having this visualization is that you can actually see the effects of things that you've skipped over. So I don't show what a heap remove min, I don't tell what a heap remove min does, but you can see the effects, at least everything you need to know for this concrete execution. As we're going to see in a second, these literate traces are actually built from the code itself. So when I built that HTML page, the build system literally runs a copy of the program in GDB and extracts the state into HTML. And similar, like the LaTeX interpreter is actually sending out to some GDB process and saying, what is the state right now? So one is like it's fun, but also it's correct by construction. So as long as your visualizations are being taken from the running state of the program, you're not lying to yourself in some sense. I wanted to mention some sort of like prior concepts here. You may be familiar in the education sphere with PyTutor. This is like a cool single stepper for Python. And the basic thing here is we're saying that's great and students love that sort of thing to see exactly what's happening. Can we scale it up from a 10-line Python program to Git or GCC or whatnot? It seems like to some extent we actually can. And then in comparison to literate programming, so obviously that's where the namesake kind of comes from. Literate programming is actually a technique for programming. So this is something that I didn't really appreciate so much at first before reading more about it, is that Knuth really views literate programming as a way of programming. He thinks that if you write your program as a literate program, then your code itself will be better. And so literate programming is really a way of making code that doesn't exist yet better as you're writing it. And the question here that we're saying is like, if we accept that there's this big chunk of code that's not going to change much, how can we make that code more understandable? Okay, so just some things to think about. Let me give you a sense of how it actually works, like how you make one of those traces. So this is the demo area, so we can feel free to oh man, yeah, that's horrible. Is that any better? I'm not sure I can, is the big problem here. Okay, why don't we just do this? Why don't we instead just walk through the quick start, because I think the quick start will show you all the code, basically. So here's how it works. If you go home today and you want to try your hand at making one of these documents, what you do is you clone the Git repo. It's on my website here. You go in, I've already got a template example in the examples directory. And then you delete mypackage.py. You don't have to do that if you don't want to. Okay, so then you need some code to trace, right? And for this little demo here, we're just going to trace this like dumb linked list program. So it just creates, you've got linked list nodes, and then you loop over and create a linked list of 4 items. So you go ahead and just in your little directory for your trace, you go in source test.c, and then you dump this program in there, and then when you run make, it'll build it. Okay, so you've just got this program, and it's built with debug symbols and everything. Okay, now you're going to write an HTML document. This is probably unlike any HTML document you've written before. Okay, and the reason is because you do some random stuff here that it's not only HTML plus some LaTeX syntax, but it's also HTML plus some LaTeX syntax plus some GDB. Okay, so it's a lot of different stuff going on here. But basically, it's an HTML document, and then in random places, you can say things like, set the executable to be traced. Okay, and this is just source/test is what we built from that C file earlier. And then you can say initialize some TReX modules, right? So the print code plugin or the GDB eval plugin. Okay. Then you just continue writing your HTML document. And when you want to print out some source code, you just use print code, and it's going to use pigmentize to pretty print that code. This HL here means highlight line 11. And then you continue writing your document, and you can use, for example, the run until command. So while this HTML file is being compiled, GDB is running in the background, and you can control GDB. So you can tell GDB, run that executable until it gets to line 11. And you can say the first time line 11 is reached, write out that node is equal to, and then evaluate the symbol node. Okay? And then you can run to line 11 again, and say on the second time it's reached, it has this value. So this is really just a normal HTML document with some of these commands. Unfortunately, the screen sizing in Zoom here doesn't play well with my bad CSS abilities. But as you see, what you get out after compiling that is it has printed some of the source code. It says on the first time it's reached, node is null, which makes sense. On the second time it's reached, node is some non-null pointer. Okay. Now let's talk about how do we make some of those visualizations. Right? So for this, we're going to use a custom TReX module. So we're going to initialize this module called visull, and then after running the loop a few more times, we're going to visualize we're going to call llviz node. Okay, so what is visull? Visull is just a Python file. So all TReX modules are just Python files. And this Python file gets to interact with the GDB Python API. Okay, so you can see here, this is the GDB Python API. It's parsing and evaluating whatever you pass in as the start node argument. Okay, so when we called visull, we pass node. So that tells it to evaluate the node variable in the C file. And then we can just loop through the linked list in Python. And as we loop through, we're creating sort of graph nodes using the TReX graph interface. And then we return this dictionary saying the sort of HTML view of this response is, whatever the graph's HTML code is. Okay, and then we add this TReX command decorator to tell it this is a command that should be available to TReX documents. So after we do that, we're returning the HTML code for the visualization, ta-da, we see the linked list visualized at the end. And this visualization is correct by construction. It's extracted from the actual running instance of the code. I also showed you the single steppers, and so the single stepper thing is just another TReX built-in package. And so the syntax for using it after you import it is that you do \single stepper, you add some optional arguments. In this case, it says single step until you reach line 16. And then you tell it what lines to actually show the single stepper for. So basically in that clicker, you're going to see a frame in that clicker every time it reaches line 10 through 15. So in your single stepper, you don't actually have to show literally every line that's reached. You can sort of keep it at a certain level of abstraction. And then inside the second non-optional argument is just what is going to be displayed for every step of that single stepper. In this case, it's going to say at this line, node is blah, 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 and then the visualization of the node itself. Okay? And so then if you compile that, what you'll see, and it's a little bit of an L because it's zoomed in too much, but what you'll see is that the single stepper is stepping through, and as we go through the loop, we're going to see node actually build up the list. And so it's actually, for once you get the hang of it, it's less surprising, but this is basically how it looks. Okay. I wanted to say a little bit about describing diagrams. So describing diagrams like those graph things is much harder than you would think. I always thought there should be some super simple DSL. You just describe I want my objects are the nodes in the graph and the pointers are the edges. It should be that simple. It is absolutely not that simple. Okay, I could not get a good DSL for this, and I would beg you to try to design one if you can. So here are some things that I ran into. First of all, the edges in your graphs that you get out trying to describe the state are not always pointers. So for example, in the Vim line tracking setup, the way that blocks are connected is by block IDs. And some of those blocks aren't even in memory, they're on disk, right? Big pain. Or in a Linux red-black tree, some of those edges are pointers to the interior of an object, not the object itself, right? And they use container of. Or they're just indices into arrays rather than actual pointers. Okay. On top of that, nodes in these visualizations aren't always objects, right? In the trace of Git, those nodes may be files on disk, or they might be compressed files on disk, and you have to decompress them first before showing them to the user. Again, they might be indices, or they might even just be variables in some decision trail in Minisat, right? Pointers aren't always pointers, and types aren't always types, right? So if you have a tagged union, the system that is trying to visualize the state of the program needs some way to know which of those union options it should pick to visualize. And on top of that, you have bit packing for red-black trees. They stuff the red-black bit in the pointer. You have things that are like header structs, so you don't actually know the type even though you think you do. It's a big pain. And on top of all of that, you need a lot of control and predictability over where nodes are positioned, right? Because if you try to use GraphViz, for example, to print out your graphs, what you're going to see is that when a new node appears, all the other nodes are probably going to move around. And if you're single-stepping and you're trying to track what happens to this node, you're going to get confused, right? So all of these things made this problem much, much harder than I thought it would be. And so right now, I basically have no solution other than you can write Python, and I have a graph API, and you write Python that turns the GDB state into a graph. And I would really, really love to have a much better DSL for this, but I so far have been kind of unable to capture all of this annoyance in a language. The other thing you may notice here is that I have all these run until this line stuff. And so if your code base changes and the line numbers change, it gets screwed. This is kind of painful. I think two things with this. One is that apparently Git can do a very good job of tracking lines over time. So I think it should be relatively easy to have an auto fixer for this. It's also sort of a feature. So you might imagine integrating build the documentation as part of the CI. And so if the code changes, it kind of forces the user to also change the documentation. Okay, the last major thing I want to say here, this is the last slide before the summary, is just that, I hope that all of you will go and try reading one of these traces, and maybe you'll get a little something out of it. But even if that is false, even if I'm the only one who ever in the world in history will ever read one of these things and it has no value for anyone else, I actually think it still has value for the writer of the literate trace. Okay, so I think the way that I like to think about it is that it gives your hands something to do while reading code, right? I want to read Vim or whatever, but I read it and am I understanding it? Am I getting anything out of it? Who knows, right? And so giving your hands something to do and saying it kind of turns the process of reading code into writing code, right? Writing this trace. And it's cool at the end of the day to say, I spent a week learning about this and now I have this, document out of it. And really, it also kind of keeps you honest, right? You might think you understand how this works. You might think you understand how this tree is encoded, but once you go to actually, extract a diagram from it, you're like, oh, I did not understand that at all. Cool. Okay, so I guess we did wait until the end for questions. I'll just say, in terms of if you found this interesting at all, I have an increasing list of difficulty things you might imagine doing. The basic one that I just want to say is if you go to this site, you can see a bunch of traces. Maybe you're mega bored on the plane home. If you read one and if you have thoughts of how it really didn't work or it really did work or how it could be made to explain things a little bit better, send me feedback. I'm a super novice writer, so any thoughts are appreciated. But yeah, happy to take questions now. Thanks.
So, go ahead, please. Hi, thanks. Great talk. So I have three things, actually. I'll make them quick. First one is the problems you mentioned about drawing diagrams automatically. This is kind of what my whole research direction is at the moment, so we should talk afterwards.
Yes, we should.
The second thing is, so when you say trace, the first thing I thought of before you presented what you did is kind of the extreme limit case of putting a print on every line of my code, right? And that looks a little bit different from a stepper in that in a stepper I'm still seeing the source code as it was, but in this print trace I am seeing a history of execution where it might be the same function calling itself, but every time it calls itself, I'm going one level deeper or something. So I'm wondering, have you thought about traces in that sense of the word too?
Yeah, so I think this notion of like, what do you do, for example, when you hit like recursion and you want some notion of call stack as well, I think is something that I haven't looked as much at. You can imagine having like a call stack on the right-hand side, for example. But yeah, we're definitely, I haven't thought much about this notion of like putting a print statement at every line, but I would love to chat more offline and hear about it.
Yeah, so we have another project in our lab at the moment which is trying to build this sort of tool, which is simulate print statement at every line and what's the right interface to deal with it. The third thing I wanted to say is that, have you heard of a tool called Electreon?
I don't think so.
So it's also a previous project from someone in our lab, where it's like literate tracing but for interactive theorem provers, where often the way you read an interactive theorem prover script is by stepping through it in the prover itself, and it shows you the states on the side. But what if you don't have access to that? What if you want to have a reified object, as you said, of what the proof looks like? And so Electreon is a tool that will record those outputs and make them visible as a web interface. So there might be some related ideas there too.
Yeah, I really love this, and it sounds like I should learn a lot more. Which group is it?
This is the System F lab at EPFL, led by Clément Pitt-Claudel. That's
Cool.
my PI.
Yeah, I'd love to chat more and hear about all this great work you guys are doing. I think especially if you have a way of extracting these kinds of visualizations, I think that would be super useful. In terms of this, one thing this reminds me of the printf on every line is that one place where that became a little bit helpful, because it's also sort of similar to like record and replay. And so, for example, for doing like operating system code or where there's like a lot of timing involved, we found that like using a record and replay debugger was actually super necessary there. So maybe it intersects a little bit there.
Yeah, for sure. Yeah, let's talk after. Yeah, thank you.
Thank you.
Yeah, so I was also going to mention the Electreon thing, but there's also some work that was presented, I think, yesterday at SOSP in Korea, a paper called Ghost in the Android Shell, where basically they add to a hypervisor instrumentation that in particular sort of prints the state of the thing as it goes, the logical state. I don't think they can do it purely through debug info. They need sort of extra instrumentation, but I think you should look it up.
Yeah.
But this was a comment. My question is, have you thought about sort of linking these traces with like sort of unit tests? Because in a sense, the unit test, they should sort of go through, and sort of, the assertion at the end should hold, but also they should go through in the sense of the right thing should happen, and a good unit test should also be sort of illuminating for the user. So have you thought about sort of doing like regression visualizations?
Yeah, so I think one thing that this reminds me of is definitely this concept of like putting the documentation into the CI in some sense, that like maybe some of your unit tests are actually traces, and when the relevant code changes, you have to fix your trace and kind of like keep it all up to date with the code itself. And so that might be a little bit in that direction. But yeah, I think it's an interesting idea.
Yeah, and I just final comment. Having many times done the job of taking a large piece of software and then for my colleagues, like writing this huge trace of like, okay, if we take this execution, it starts from this function, it goes there, it does this, it goes there, it goes that, then like an inline LaTeX formula, like this is great work.
I'm glad to hear it. Yeah, definitely give it a try and email me with your hate if it doesn't work for you.
Will do. Thank you.
Yeah, let's do it.
Thanks, Matthew. That was really nice. Just to remind myself, to remind you, some of your problems to do with pointers into the middle of things and things like that, I have some work that might be able to help with that, so I'm going to ping you after, or if I don't ping you, ping me. But the other thing is, I feel like with documentation, there's a sort of something a bit like the tech transfer problem, which is people do enough work to solve their immediate problem, and then there's an extra level to make it sort of digestible by other people, and that's sort of a gap that's really hard to bridge. So I don't know if you've thought about any extra layers of tooling that could, like for example, if I had a whole GDB history where I was stepping through some tricky thing, like could it like generate a first draft of a literate trace for me or something like that? Have you thought about that problem?
Yeah, so this is actually something that I would really love to have, and going the other way. So sometimes you're writing this literate trace and you're like, oh, I want to see what's going on. I just want to open like this literate trace position in GDB to interact with it, and exactly the direction you're saying of like, I've done all this to understand it, I just want to dump it into a trace to send it off to someone else or as like a first draft. And I think that's doable. I haven't done it yet, but I would love to do that, yeah.
Cool, thanks.
Hi, thanks for the talk. Have you considered reversing the control, as in now you describe which lines you want to track and you comment on them? Could you have the code, something in the code directly that says you must comment on that state?
Yeah.
And then it will be kind of, so it's automatically up to date because the code is always good. And
yeah, so I'm working on something a little bit like this, of like extracting some of these visualizations by putting things into the code. I'm not sure where I think like, in terms of a sociological thing, I want to be able to write traces for other people's code as it sits, like the code in their Git repo or whatever. So doing it out of band like this is helpful for that. But I definitely think that what you're suggesting of putting things in the code itself, maybe if you have more control over the project, is the right way is a reasonable way to do it as well. Yeah. Thanks.
Okay. Are there any further questions? Then just thank the author.